Hi, my name is Alyssa Murphy, and this is my presentation for Lab 4 Oscillating Motion for Physics 2211. So here's a brief table of contents. First I'll be going over an introduction, then I'll go into the tracker video, then the computational model, and then error and questions. So the purpose of this lab was to use Newton's second law and the energy principle to analyze oscillating spring motion and to compare the experimental data with a Python-predicted model of the motion. The data is then used to create energy graphs of the system. So the concepts that will be used in today's lab are the Newton's second law, which finds that the net force on an object is equal to the change in momentum over the change in time, which can be used for calculating position and velocity update. We'll also be talking about the energy principle, which finds that if there's no net change in energy, there's no work done by the surroundings on the system. The total energy of the system is the sum of all kinetic and possible energies. The equations we'll be using today are net force, which is F net equals delta P over delta T, velocity update, which is V final equals V initial plus F net over M times delta T, and position update, RF equals RI plus V average delta T. We'll also be going over the energy principle, which is delta E equals W plus Q, gravitational potential energy, which is mg delta Y, spring potential energy, which is 1/2 Ks delta S, and translational kinetic energy, which is 1/2 mv squared. So for a preview of the results, the glow script model resembles the experimental data. However, the x-direction graphs are more similar than the y-direction graphs. And the energy graph shows that this energy principle is satisfied when the system is considered to be everything and no surroundings are present. So going into the tracker video, the system in this experiment is going to be the Earth, the spring, and the mass, so it's going to include everything, and the surroundings are going to be nothing. The initial conditions were found to be negative 0.104, negative 0.6330 meters for the position, and the initial velocity is the zero vector, and the mass is 0.402 kilograms. So here's the video with the tracking done on it. So then going into the computational model, first I changed the mass based on that known value of 0.402 kilograms. Then I changed the initial position to be from the tracker data, and then made delta T very small. The spring constant and length were found from video observation, and then L is found by subtracting the spring position from the ball position, and then down here these system energies are calculating using the equations that we talked about earlier. In the second part of the model, the calculation loop, up here I set T to be less than the total amount of time for the tracker video. The initial energies are defined here in order to calculate change in energies later. Here we calculate the gravitational force, which is negative mg, and then the spring force here is negative Ks times S times L hat. The net force would be the combination of those two, and then down here we use the momentum principle to update velocity and position, using the equations that we talked about earlier, and then here the spring position is updated within the loop, and then here these energy changes are calculated based on these initial energies that were calculated up there. So here are the graphs. This graph shows this orange line being delta E shows that the combination of all the potential and kinetic energies is coming down to be 0, which does not violate the energy principle. And then here we see the x position and y position graphs, again seeing that this y position graph is a little less accurate than the x position graph. So going into some error, the possible sources of error would be the tracker video. It's possible that the tracker was not placed directly at the center of mass in every frame of the video, which could lead to slightly incorrect position data like we see with the x and y graphs. And then there was no drag force accounted for in this lab, and it's possible that if the internal kinetic energies were accounted for, aka like using a real system, the answer might be different. So to answer the what does it mean questions, first, is the energy principle satisfied? Yes, we see this because the total change in energy is 0, and these two potential energies, which we see in this graph, continuously oscillate, and the kinetic energy generally cancels out the value of the potential energies. And then the x position oscillation period was found to be 1.52 seconds, and the y position was found to be 1.6 seconds. This could have been caused by incorrect tracking or the drag force that we talked about earlier, which this is going to impact the calculation of the spring constant and the spring potential energy. Thank you very much.